Hello everyone, and welcome back to the Intermediate Algebra video lecture series. Today we are going to be covering how to solve radical equations. So a radical equation is an equation that contains some sort of radical. So what we're going to focus on in this course is radical equations that contain square roots, although as we're going to see in the next section, there are other types of roots, and you'll be solving radical equations that cover other types of radicals in college algebra. So the goal of solving a radical equation is to solve for the variable, and the variable is going to be inside your square root. So to get the variable by itself, you have to eliminate the radical and then continue to get the variable by itself. So to solve a radical equation, we're going to use these four basic steps. Now, the first step is to isolate the radical on one side of the equation, if necessary or possible. So basically, you're going to try and get whatever the square root is by itself on one side of the equation, if you even need to do this at all, or if it's even possible. Then, once you've got the radical isolated, you're going to raise each side of the equation to the same power to eliminate the radical. What this will do is when the radical and the power cancel each other out, you will be left with some sort of equation that you can solve, some sort of polynomial equation. Now remember, the power that undoes square roots is squaring. So you're actually going to be squaring both sides to cancel out the square root. Then you're going to solve whatever polynomial equation you now have by using, previous techniques that you have learned before. Now this fourth step is necessary. You might remember back in rational equations, we could have the possibility of extraneous solutions. We're going to see that here too. So each and every single time, no matter how perfect your algebra is and no matter how confident you are in your final answer, you must check your solution. Because if your solution does not actually satisfy the equation, you have what is called an extraneous solution, which is a number that looks like it should be a solution but doesn't actually work when you check it. And you're going to eliminate any extraneous solutions that do not satisfy the equation. There are some of these equations that are going to have no solution, so watch out. You must check your answer every single time. So what we're going to do for this first one is we're going to solve it. Now you might notice that the variable that we're trying to solve for is inside of a square root. You cannot split up the addition inside of the square root, so this is all stuck together until we get rid of that square root. Now let's check. Is the radical by itself on the left side of the equation? Is there anything on the left side of the equal sign that is not in a square root? Well, there isn't. So the square root is already by itself, so step number one here is already done. So what I'm going to do is I'm going to take both sides and raise both sides to the same power that will cancel out the radical. So what power cancels out a square root? A squared. So I'm going to take both sides and I'm going to square both sides. Notice how whatever you do to one side of the equation, you must do the exact same thing to the other. And notice how I used parentheses, because the entire side of the equation is being raised to the second power. So then on the left, square root and square are going to cancel each other out, leaving you with what was inside the radical, 3x plus 1. And then on the right, don't forget that whatever you did to one side, you need to do to the other. So 4 squared is 16. Then this is a linear equation that you can solve. So I'm just going to subtract 1 from both sides, gives us 3x equals 15. Divide both sides by 3, and we get x equals 5. And notice, I'm not going to circle this yet, because for each and every single one of these, you must check your solutions. So to check your solution, you're going to plug in your potential answer into the original equation in for every single spot you see in x. So I'm going to plug 5 into the original equation in place of that x, and I am going to simplify and see what happens. Now remember, anything that is inside of a radical needs to be simplified first. So 3 times 5 is 15, plus 1 is 16. Square root of 16 is 4. 4 does indeed equal 4. So since we got the same number on both sides of the equal sign, that means 5 satisfies the equation, and then that means 5 is safe to circle as our final answer. Now, for this next one, the radical is not by itself on the left side of the equation. So before you do any squaring, you need to make sure that the square root is by itself. So this minus 7, which is not inside of a square root, really needs to move over to the other side. So I'm going to move this over to the other side by adding 7 to both sides. So I will get the square root of x minus 2 equals 0 plus 7 is 7. Now that the square root is by itself, now you can square both sides. So I'm going to take both sides, wrap both sides in parentheses, and I'm going to square both sides. Now on the left, square root and square will cancel each other out, leaving you with what was inside the square root, x minus 2. And then on the right, don't forget that whatever you did to one side, you need to do to the other. So 7 squared is 49. Then I'm going to finish getting x by itself by adding 2 to both sides. And that gives us x equals 51. So before you circle it and call it good, you do need to check your solution. So you're going to check your solution by plugging in 51 into the spot that you see in x in the original equation. So I'm going to plug in 51 for x, and I'm going to simplify this using order of operations. Anything that is inside of a square root has implied parentheses. Parentheses always go first. So 51 minus 2 is 39. Then after parentheses come exponents. Remember, square roots count as exponents. They're done at the same time. So I'm going to do that square root next. Square root of 49 is 7. Then I'm going to finish up with the subtraction. 0 does indeed equal 0. So since we got the same number on both sides, that means x equals 51 is our final answer. Now for this next one, we're going to start off the same way. We're going to first isolate the radical. So I see this plus 3, which is currently not inside of a square root. Anything that is not inside of a square root needs to move to the opposite side of the equation. So I'm going to first subtract 3 from both sides. So that will give me the square root of 2x minus 5 equals 0 minus 3 is negative 3. Then we're going to get rid of the square root by taking both sides, wrapping both sides in parentheses. The parentheses are extremely important here. And we're going to square both sides. Then on the left, square root and square cancel each other out, leaving you with 2x minus 5. And then on the right, negative 3 squared, because the negative is inside the parentheses, the negative is also getting squared. So negative 3 times negative 3 is positive 9. Then we're going to finish solving for x by adding 5 to both sides. So we'll get 2x equals 14. Divide both sides by 2, and we get x equals 7. Now, before we do anything, before we move on, we do need to check our answer. So I'm going to check my answer by plugging 7 back into the original equation in for where you see an x. So I have the square root of 2 times 7 minus 5 plus 3. We're going to see if that equals 0. So I'm going to simplify what's in the square root. 2 times 7 is 14. 14 minus 5 is 9. Then we're going to take the square root of 9. Square root of 9 is 3. And 3 plus 3 is 6. And 6 does not equal 0. So since 6 does not equal 0, that means 7 does not satisfy the equation. So this solution actually doesn't work when we go back and check it. This is what is called an extraneous solution. It looked like it should work. We did our algebra perfectly, but when we actually checked it, we clearly got something that didn't work. So we're going to eliminate this extraneous solution, and since this was our only solution, our only potential answer, this equation has no solution. So these will come up once in a while. Be prepared for them, be on the lookout for them. That is why you must check your answer to these equations every single time, no matter how confident you are. No solution can sneak up on you. So what we're going to do for this next one is we are going to solve for x, which is currently inside of a square root. So I'm going to first isolate the radical, so anything that is not underneath a radical on the left side of the equation needs to move over to the other side. So I'm going to move this 2 by subtracting it from both sides. So I will get the square root of 3x equals 5 minus 2 is 3. Then I'm going to get rid of that square root by taking both sides and squaring both sides. So then square root and square are going to cancel each other out, leaving you with 3x equals 3 squared is 9. Then finish this up by dividing both sides by 3, and we get x equals 3. And as we just saw, we do need to check our answers every single time. So I'm going to check my answer by plugging 3 back into the original equation in for where you see an x. So I have the square root of 3 times 3 plus 2, and we're going to see if that equals 5. So 3 times 3 is 9. Square roots come before addition, so square root of 9 is 3. 3 plus 2 does indeed equal 5. So since this 3 satisfied the equation, that means 3 is our final answer. Now for the next one, the square root is already by itself on the left side of the equal sign. So since the radical is already by itself, I'm going to jump right into taking both sides, wrapping them in parentheses, and squaring both sides. Square root and square are going to cancel each other out, leaving you with 2x minus 3 equals 0 squared is 0. Then I'm going to finish getting x by itself by adding 3 to both sides. So I get 2x equals 3. Then I'm going to divide both sides by 2. Yes, you can get a fraction for an answer. We get x equals 3 over 2. So then we're just going to check our answer to make sure that this actually works. So I'm going to plug 3 over 2 back into the original equation in for x. So I'll have the square root of 2 times 3 over 2 minus 3. We're going to see if that equals 0. 2 times 3 over 2 is going to be 3. 3 minus 3 is 0. You can take the square root of 0. You have to ask yourself, what number times itself is 0? Well, 0. So the square root of 0 is 0. And since we got the same number on both sides of the equal sign, that means x equals 3 over 2, satisfied the equation, and is our final answer. Now for this next one, if you have two separate radicals, as long as they are by themselves on each side of the equation, this one is still pretty doable. Now there's no isolating the radical here. That's not really possible. We've got two of them. But what we are going to do, since you notice that there is nothing in this entire equation that is not inside of a square root, I am going to simply jump into taking both sides, wrapping both sides in parentheses, and squaring both sides. So on the left, the square root and the square cancel each other out, leaving you with what was inside the radical, 3x plus 4. Then on the right, square root and square will cancel each other out, leaving you with what was inside the radical, 7x minus 4. Then this is a linear equation with variables on both sides. So I'm going to move all of the variable terms onto one side of the equation. So 3x minus 7x is negative 4x plus 4 equals negative 4. Then I'm going to subtract 4 from both sides. Gives us negative 4x equals negative 8. Then divide both sides by -4, and we get x equals 2. Then, before you call it good, you do need to check your answer by plugging your solution, 2, back into the original equation into every single spot you see in x. So since there are 2 places where x occurs, you're going to plug a 2 in here and a 2 in here. So we're going to get the square root of 3 times 2 plus 4, and we're going to see if that equals the square root of 7 times 2 minus 4. So 3 times 2 is 6. Then on the right, 7 times 2 is 14. Then 6 plus 4 is 10. 14 minus 4 is 10. I really don't need to know what the square root of 10 is as a decimal, and it can't simplify, and we really don't care. As long as they have the same number on both sides of the equal sign, that means 2 satisfies the equation, so 2 is our final answer. Now, there are a ton of applications of square roots. One of the major applications of square roots is in what is called the Pythagorean theorem. So, in ancient Greece, a mathematician named Pythagoras deduced that the sum of the squares of 2 legs of a right triangle is equal to the length of the hypotenuse squared. So, a right triangle is any triangle that contains a 90-degree angle or right angle. The legs are the sides that actually form the right angle. So these would be the legs. The hypotenuse is the side that is across from the right angle. And so what this theorem is used for, it is used to find the length of a missing side of a right triangle if you were given the lengths of the other 2 sides. Now, the essential process for this is that inverse relationship between squares and square roots. Remember that the order of the powers doesn't matter. So if you have a square root with a square outside, or a square with a square inside of a square root, it doesn't really matter. These 2 are the exact same, and in either case, any time that you have a square and a square root performed together, no matter what order they're in, they're always going to cancel each other out. So remember, a right triangle has a 90-degree angle, and the legs are the 2 sides that form that 90-degree angle. The side that is opposite or across from the 90-degree angle is called the hypotenuse. So in this diagram here, A is one of the legs, B is the other leg, and then C is the hypotenuse. So the Pythagorean theorem says that a squared plus b squared equals c squared. You can also think of this as one of the legs squared plus the length of the other leg squared equals the hypotenuse squared. So what we're going to do is we are going to use the Pythagorean theorem and use square roots to find the length of this missing side. Now the first thing that you should do is you should identify whether the missing side is a leg or the hypotenuse. The legs are the sides that form the right angle. So this is our missing side x, and it is one of the sides that forms the right angle, so this is actually one of the legs. The other leg is 12, and the hypotenuse is 13. So the Pythagorean theorem says that the lengths of one of the legs, x squared, plus the length of the other leg, 12 squared, equals the length of the hypotenuse, 13 squared. So then I'm actually going to do all of the squaring. So 12 squared is 144. 13 squared is 169. Then I'm going to at least start to get the variable by itself by moving the 144 over to the other side. Gives us x squared equals 25. And then just like squares can undo square roots, you can go the other way around. Square roots will also undo squares. So I'm going to take the square root of both sides. And then the square root and the square will cancel each other out, leaving you with x equals square root of 25 is 5. So the length of that missing leg is 5. Now for this next one, remember, you should identify whether your missing side is a leg or the hypotenuse. The two legs here are actually 6 and 2 because these are the two sides that form the right angle. The x is actually across from the 90-degree angle, so the missing side is actually the hypotenuse. So Pythagorean theorem says that the length of one of the legs, 2 squared, plus the length of the other leg, 6 squared, is equal to the length of the hypotenuse, x squared. Now on the left side, I'm going to simplify using order of operations. So 2 squared is 4, 6 squared is 36, equals x squared. 4 plus 36 is 40, equals x squared. Then I'm going to get rid of that square by taking the square root of both sides. Square root and square cancel each other out, leaving you with x equals the square root of 40. And we are not going to call this our final answer, because 40 is an awfully large number, and 40 actually has some perfect square factors. So we are actually going to take a minute to simplify the square root of 40. So the perfect square factor that goes into 40 is 4. 40 is actually 4 times 10. So I'm going to write this as a product of two separate radicals, the square root of 4 times the square root of 10. Square root of 4 is 2. Square root of 10 does not have any perfect square factors, so it cannot simplify. So fully simplified, your final answer is actually x equals 2 square root of 10. So just make sure that for any of these that you always check to make sure that your final answer is fully simplified. All right, now for this next one, again, if you want to try any of these before I do them, just pause the video and resume when you're done. But for this next one, one of the legs is 4, the other leg is 8, and the hypotenuse is actually our missing side. So our missing side is actually the hypotenuse. So the Pythagorean theorem says that if you take the length of one of the legs, 4, and you square it, plus the length of the other leg, 8 squared, is going to equal the length of the hypotenuse, x squared. So 4 squared is 16, plus 8 squared is 64, equals x squared. Then 16 plus 64 is 80, equals x squared. Then you're going to finish getting x by itself by taking the square root of both sides. Square root and square will cancel each other out, leaving you with x equals the square root of 80, which can be simplified, and you will need to simplify it. So just quickly simplifying the square root of 80, the perfect square factor that goes into 80, the largest one is actually 16. 80 is 16 times 5. So you're going to simplify that by separating it into the square root of 16 times the square root of 5. Square root of 16 is 4. 5 is a prime number, so that is fully simplified. So your fully simplified final answer is actually going to be 4 square root of 5. And then for this last one, you need to first figure out whether your missing side is a leg or the hypotenuse. So your missing side is actually one of the legs. The other leg is 3. And the hypotenuse, the side across from the right angle, is actually 5. So Pythagorean theorem says that the length of one of the legs, x squared, plus the length of the other leg, 3 squared, is equal to the length of the hypotenuse, 5 squared. So 3 squared is 9. 5 squared is 25. I'm going to subtract 9 from both sides, giving us x squared equals 16. Then finish this up by taking the square root of both sides. Square root and square cancel each other out, leaving you with x. And the square root of 16 actually comes out to a whole number 4. So x equals 4 is the length of your missing side. All right, so that is it for section 10.4, radical equations and the Pythagorean theorem. For the next section is actually not in the textbook, but it is a course objective. So the next section is going to be encompassed in chapter 10, but it doesn't actually correspond with a textbook section. The next section is going to be nth roots and rational exponents. So stay tuned for that last chapter 10 video. Thank you all very much for watching, and I will see you guys in the next video.